All right, welcome everyone. Um, I'm so pleased everybody is here, either on Zoom or like watching on YouTube later. Um, so our speaker today is going to be Yael Tauman Kalai. And before I talk about her and her accomplishments and how wonderful she is, I'll start by I'm thanking all of my a TCS plus co 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 organizers, Claymont Kanan, Hanidia Day, Smega Garg, Gadam Kameth, Ilya Regenstein, Oded Regev, Salil Shram, Noah Stevens, Davidowitz, Tomal Vidic, Eric Weingarten, and David Wadge. This is a many person operation that goes on behind the scenes. And so thank you all. I'm extremely thrilled today to be introducing Yael, who is extremely accomplished. She has degrees coming out of Hebrew University, Weizmann Institute, MIT, and since then she has worked at Microsoft Research and then Weizmann again, and then she was on Georgia Tech faculty, and now she's back at Microsoft Research, and she also has a kind of MIT affiliation, and so very, very accomplished. And she'll be talking today about doing efficient verification of computation on some untrusted platforms. Thank you, Yael.
Thank you, Rachel.
And I'll say first in the audience, if you have any questions during the talk, I'll post them in the chat, and I'll be sort of moderating. And I've been told you're encouraged to kind of ask questions during the talk. And so either I'm in the chat, or if you want unmute is great. And they'll also have time afterwards for some more questions with and without recording. So thank you, Yael.
Thank you, Rachel. Thank you all for coming. And as Rachel said, please feel free to ask any question during the talks. During the talk, questions are very welcome. The goal is for you to understand. So, if something is not clear, please just stop me. So yes, I'm going to talk today about a topic that's very, very dear to my heart, a topic I've been obsessed with for many years. And the topic is on the efficient verification of computation. So let me tell you what this means, and let me start kind of with the story behind it. Oh, wait, why is this not working now? Okay, good. Sorry. Okay. So, we used to, in, ancient times, we used to do the computations on our own local devices that practically essentially looked like this. But today, with the kind of increasing computation, power, a lot of large-scale computation, and also increasing kind of small, very limited computational devices, much more of our computation nowadays are done on remote platforms and often untrusted platforms. One place where this plays out very clearly is on blockchain applications, where now there's a humongous amount of data that needs to be checked and verified. Every time we do a transaction, verifying this transaction is a function of kind of the entire blockchain, which is a huge computational chain. And so now we can't do it on our own machines. And this kind of new reality raises a whole slew of new challenges. So of course, there's economic challenges related to incentivizing and pricing. So that's far away from my area, but very, very interesting. Another very interesting question is related to privacy. And that's actually very dear to my heart as a cryptographer. How do we make sure that our data that we put out there remains private? So this is again, I think very interesting topic, but it's not what I'm going to talk about today. What I'm going to talk about today is how do we ensure the integrity? Namely, when we put out when someone does a computation for us, how do we know that the computation that's done is correct, is the correct computation? And that's kind of what motivates the problem I'm going to talk to you about today, which is efficient verification of computation. So here's my goal. What I want is the following. Let's say I have a Turing machine, which I denote by M, some computation, It can be modeled Turing machine, it can be modeled something else, that's not important. But I have some computation, I denote by M, and an input. Now, I want to delegate to someone else to do this computation for me. So I want to outsource this computation, get the result of this computation, which I denote by Y. But now I'm not sure that this Y is the correct computation. And what I want is a succinct certificate. I want some certificate that will certify that indeed this output is correct. So let me define this a bit more formally. What I want is two properties. First, I want completeness, which means that if indeed Y is the correct computation, and let's say one can compute Y, let's say within time T. So let's say the Turing machine input Y and input X outputs Y in T steps. Then one can compute this valid certificate, a valid certificate that certifies that Y is indeed the correct output in time without too much overhead, okay, because we want to use these things. So, it should be computable in time, roughly T, ideally linear in T, maybe quasi-linear in T. And very importantly, the size of the certificate in the time it takes to verify the certificate should be much, much, much less than T. Okay, and these two, the fact that the size of the certificate and the time to verify is significantly shorter than T is paramount. It's crucial, because if it takes time T to verify, then just do the computation on your own. So really, we want these certificates to be very efficiently verifiable. Okay, so that's kind of the completeness. And the soundness we want is to say, okay, nobody can fake a certificate. So a little more formally, what we want to say is that if Y is false, it's not the correct output, then it should be practically impossible to generate a valid certificate. And what I mean by practically impossible, essentially what I mean is, well, if someone can do this, can generate a fake certificate of a false computation, a false output, then he can break some cryptographic assumption. So then it can break factoring or other, LW assumption, whatever your favorite kind of hardness assumption is. Now, at this point, here's the question I expect people to ask, which is, why practically impossible and why introduce cryptographic assumption here? Why not just ask for like true soundness? Namely, if Y is the incorrect answer, then it should be straight out impossible to generate a certificate. Why this practically and only computationally bounded that cannot break the assumption, cannot cheat? So, right, why not just say, oh, it's impossible, period, to prove false statements? And the reason we can't just say it's impossible, because that's too much to hope for. If you get rid of the practically and just say impossible, then it will essentially mean that any time T computation has a succinct certificate, a succinct witness. Having a succinct witness is like saying it's in n time, non-deterministic time, much smaller than T. And we don't believe this is the case. We don't believe that D time T is contained in n time much less than T. So in other words, the reason we require only what we call computational soundness, to say that only a computationally bounded adversary cannot break the scheme, is because that's the only thing we can get. Okay? So again, so what we want is to say that a computationally bounded adversary, one that cannot break some underlying cryptographic assumption, he cannot generate a false certificate. But let me tell you, false certificate exists unless D time T is contained in n time much less than T, which we do not believe is the case. Okay. So that's kind of our goal. This is what we want. And just to say, to achieve this goal, we assume that both parties, the party who generates the certificate and the party that verifies the certificate, share some kind of common random string. Okay. Essentially, you could say, first of all, what is this common random string? Where did it come from and why do we need it? So let me just say, in the schemes you'll see today, most of the talk, you can just assume that this common reference string is just some description of a hash function that they agree upon. So it's something quite benign. The reason we need this is here, essentially, we're going to encode our hardness assumption in a sense. But just think of it as a hash function. It's going to be a description of a hash function. And in practice, when these things are used in practice, there is, often we just use kind of SHA-256, some off-the-shelf hash function. For those who don't know what SHA-256 is, it's really not important. It's just a standard hash function that's people use. Okay, so that's our goal. Our goal is to construct this thing. We have a common random string that we agree on. The prover who generates the certificate and the verifier who verifies. We want to find the mechanism for which a prover can generate a succinct certificate with the guarantee that it's very hard to forge. Namely, you cannot forge the certificate unless you can break some cryptographic assumption.
Is there like another theoretical reason why we might want this common random string, like essentially what you suggested with D-time?
Yes, exactly. Good. Very, very good question, Matan. So let me just say, without this common random string, we fall into the same impossibility result. So you must have a common random string. And intuitively, or maybe not intuitively, but the high-level reason why that's the case is without the common random string, there is no place to embed a cryptographic assumption, and then there's no place to hope to get computational soundness. Without it, you're kind of stuck with statistical soundness. And then we get the same impossibility result. So the answer why we need a common random string is without it, we're stuck with the same negative result, essentially. Thanks for the question. Okay, so this kind of scheme, this scheme is called a succinct because the certificate is succinct, non-interactive because it's just a certificate. It's not like an interactive proof or anything like that. And argument. Argument is another word for computationally sound proof as opposed to statistically sound. So this is called a succinct non-interactive argument, and we call it SNARG for short. So if those who've heard the kind of jargon SNARG, that's what they're referring to.
Is that any different than a snark? In a sense,
yes.
I've also heard that around, yeah.
Yes. So there's also a related notion of a snark with a K, and that refers to some knowledge. K refers to knowledge. So succinct non-interactive argument of knowledge. So we're not going to talk about knowledge today, but a lot of these works actually are concerned with knowledge and so on. So but I'm not going to mention it in this talk.
Yael, there's a question in the chat. Can you explain again what is the difference between statistically sound and being computationally sound?
Yes, thanks for the question. So statistically sound just says nobody can cheat. An adversary, no matter how powerful he is, it's not an adversary, even an all-powerful adversary cannot cheat. Computational soundness just says an adversary that's computationally bounded, like a polynomial time adversary, or an adversary that cannot break factoring, or cannot break our underlying assumption. These kind of adversaries cannot cheat. So as long as you believe, let's say that factoring cannot be broken in polynomial time, then you get security against polynomial time adversaries. So that's what computational means. It's only against computationally bounded adversaries. That's what computational soundness is. Okay. So is the goal clear? Okay. So with that, can we achieve it? So let's see. So first, constructions. Do we have SNARGs? And so let me tell you, this kind of line of work actually started way before this kind of blockchains or cloud computing came about. It started actually already in the early 90s by really beautiful works on interactive proofs, multi-prover interactive proofs, PCPs, and so on. And all these works, the focus was actually on high complexity classes and statistical soundness. Okay, actually, these works actually originally started by Goldwasser, Mikhaili, and Rakov with the goal of doing actually zero knowledge. They weren't at all interested. They just wanted to get secrecy. And to get secrecy, they defined this notion of interactive proofs. And once interactive proofs were defined, that's like, oh, what's the power? And then there was kind of a rush to try to understand what's the power of interactive proofs. And then again, Benno, Goldwasser, Kilian, and Wigglesworth defined the notion of multi-prover interactive proof, where there's two provers. And there was a rush goal to understand what's the power of this model. And then PCPs came about, probably checkable proofs. And there was kind of a whole slew of beautiful, beautiful works where the focus to kind of understand the power of these proof systems, interactive proofs, multi-prover interactive proofs, PCPs. And in all these, the focus was actually on high complexity classes. Can we do P space? Can we do X? Can we do, these high complexity classes and only statistical soundness? Okay, but then in the early 90s, actually there was the first construction of a SNARG. So exactly what I defined, it was a heuristic, it was constructed. and beautiful works by Kilian and Mikali. So, however, these works had two drawbacks that I'm going to talk about. So the first, it was pretty heavy in terms of computational cost to generate the certificate. So it wasn't practical in any way. But more importantly to this talk, there were some security issues, which I'm going to mention as we go along. Okay. So that was all early 90s. In 2008, together with Shafi Goldwasser and Guy Rothblum, we defined this notion. This is kind of when cloud computing just started, we're kind of in the diapers, and we were like, oh, maybe one day people will use these things. So we defined this notion of what we call doubly efficient interactive proofs. And the focus of that work was really on real world computation. So computations in P, like polynomial time computations. So whereas the previous line of work, the verifier was always modeled as a polynomial time machine, like efficient, which, in complexity theory, we think of as polynomial time. And the prover was kind of all powerful. It was even in one of these works, it was named a Merlin, like a wizard. Like the prover was thought of as being all powerful, the verifier polynomial time. And in this work, we were thinking, no, even the verifier is not actually what we want to delegate is polynomial time, because in the real world, everything is polynomial time. But we want the verifier to be just really, really efficient. So let's say linear. And the prover should not have too much blow up. So here's the goal. We want verifier to be super efficient, and we want generating a proof to incur a minimal overhead, which is essentially how we define the completeness, right? We said generating the certificate should incur minimal overhead. Let's say generating it takes time, maybe linear or quasi-linear, in the time it takes to do the computation itself. So that was kind of our goal. And we gave a construction, actually an interactive proof. It's not a snark, it's actually it's kind of an interactive proof that has this double efficiency. And again, double efficiency, it talks about usually not only the verifier efficiency, but also the prover. That's the double, okay? Because in previous work, there was no kind of focus on prover efficiency. So we've constructed this double efficient interactive proof for bounded depth computations. Okay, and this is referred to the GKR protocol, so I'll call it the GKR protocol during this talk. Okay, so this is interactive proof. It's not a snark, which is a non-interactive, but one can convert it easily into a snark using the Fiat-Shamir paradigm. And I'm going to talk about this as well as we go along. Okay, so that was a snark construction from this work. And what kind of was nice about this work is that the construction was actually very efficient. It was very simple, really simple and efficient. Kind of uses just kind of basic algebra kind of okay. After this work, there's been kind of a explosion of work. I think also due to the kind of change in the world where, kind of cloud computing became a thing, seemed like a thing. It was actually before even blockchains came about, but there were just tons of work in this area, some based on really beautiful theoretical ideas, some actually applied work. And there's been a lot of prototyping of these works, some based on GKR, some on other protocols. And not only prototyping, it was actually deployed. Okay, and today these works are used by various blockchain companies. For example, Ethereum uses them today and others as well. Moreover, there's even like the biggest funding agency for kind of in crypto, which is the DARPA agency. They have like a huge call now, spending a lot of money and trying to come up with secure and kind of efficient snarks. In particular, their kind of focuses on post-quantum security, which is important as well. But these things are really, really heavily studied. Our community is fully engaged in this, and a lot of work, and all kind of from the most theoretical to the most applied and deployed. Despite all this work, until recently, all the snarks we had were only heuristically secure, which is pretty shocking. Okay, we worked on this for many years. We have hundreds of papers on this topic, but only recently we were able to actually guarantee, like at least understand the soundness of the schemes we use. And this is what I'm going to talk to you about today, how to get provable security, okay? And again, what we want to say is not just, oh, we hope nobody can fake certificates. We believe nobody can fake certificates. We don't know how to fake certificates. What we want to say, no, we cannot fake certificate unless factoring is in P, or unless LWE is in P, or whatever. For those who don't know the cryptographic assumptions, it doesn't matter at all. But we want to reduce, say, if someone can break, then they can break a well-believed cryptographic assumption. So that's kind of our goal. Okay,
So,
any questions?
I have a quick question. So I'm sure you're going to touch on this, but is this gap because of the Fiat-Shamir?
Yes. Yes,
okay.
I'm going to touch on that. Yes, but
okay,
partly
right,
it's because of the Fiat-Shamir paradigm. That it's a heuristic itself.
Right.
Yes.
So everything else is probable secure. It's just the paradigm itself.
Well, the ones that are based on the Fiat-Shamir, yes, but there's also other snarks that are not based on Fiat-Shamir. So,
and they're still heuristic?
Yes. Well, they used to be heuristic. So I'm going to talk about that.
Okay, got it. Thank you.
Yes. Okay, great. Any other questions? Okay. So what's the plan? So most of the talk today, the rest of the talk, I'm going to focus on this. I'm going to talk about the GKR protocol and show how to convert it into a snark in a secure way. Okay, how to get provably secure snark from this GKR protocol. I probably won't have much time, but maybe I'll have a bit to talk about a second line of work, which actually constructs snarks from a different primitive, not from doubly efficient, not from interactive proof, but rather from a multi-proof interactive proof. And these kind of use special multi-proof interactive proof that have kind of special soundness. It's called non-signaling soundness, which is motivated from or studied in the realm of quantum information, which this works have nothing to do with quantum, but somehow we found this magical connection between these kind of crypto and quantum information. So hopefully I'll have a few minutes to talk about that as well. But we're going to start with part one. So sorry, but just want to say a few words that in this process of kind of constructing snarks, it's been really interesting because we found a lot of connections to other problems, other fields that have nothing to do with snarks. And we found other applications in cryptography that have nothing to do with snarks. So that was really interesting. I won't have time to talk about these applications, but just want to mention like applications such as hardness of approximating linear programs, or finding Nash equilibrium, or relations to quantum supremacy, and so on. So that was kind of really a fun journey. Okay, but let's start with kind of constructing the snark. So the first thing I want to talk about is I mentioned the GKR protocol is an interactive protocol and that we can convert it to a snark. So let me start by mentioning, how do we convert interactive protocols into a snark? And we know how to convert interactive protocols that are what's called public coin. Public coin means that the verifier's messages are just random bits. Okay, it's protocols where the prover sends a message, the verifier replies with just random bits. Prover sends a message, the verifier replies with random bits. The GKR protocol is such a protocol, but we have many other protocols that have this property. And what the Fiat-Shamir heuristic essentially shows how to convert any such protocol into a non-interactive one, how to essentially eliminate interaction. And the idea is beautiful and simple. So let me explain their idea, how they do that. So essentially what they do, they say, let's replace the verifier with just a hash function. So in other words, if we have an interactive proof where let's say the verifier sends alpha, the prover sends alpha, verifier beta, prover gamma, verifier delta, and so on. Now we're converted into a snark. The prover will send all of it. So the certificate will just contain the transcript, but he cannot choose the verifier's messages, beta and delta, freely as he wishes. That will make it insecure, not sound. Instead, he's forced to choose beta as some hash of alpha and delta as hash of the transcript so far. So essentially, we replace the verifier with a hash applied to the transcript so far. That's it. Okay, so whereas before they need to interact back and forth, you can think of it now, the prover sending a message, and then thinking of the verifier's message as being a hash of the transcript so far. Sends a message, So in some sense, instead of interacting with the verifier, he's interacting with the hash function. But the hash function he can compute on his own. So he just generates this transcript. And this transcript is the snarl. Any questions about this paradigm, this heuristic? So let me first say, where is this hash function? Who chooses this hash function? So this hash function is the CRS. And the Fiat-Shamir paradigm said, choose a hash function. And now that's how you're gonna kind of eliminate the interaction. And some hash functions are good, some hash functions are bad. You need to choose the hash function wisely. Now there's a question, for which hash function is the resulting snark secure? And that's a good question, and we'll talk about that. But that's kind of the general paradigm. Any question about this paradigm? Okay, so now you can ask, actually, why do we need, yeah,
so the interactive protocol is statistically sound here.
No, good. Oh, the interactive is statistically sound, yes.
So what does that mean?
Okay, the interactive protocol is statistical sound, which means, by the way, it doesn't have to be statistically sound, okay? The Fiat-Shamir heuristic was used also applied to protocols that are not statistically sound, and I'm gonna give you an example. But statistically sound just means even an all-powerful prover cannot cheat in the interactive proof, in the interactive protocol.
Okay, thank you.
Okay, great. But the Fiat-Shamir, as I'm going to show in a minute, was also considered for computationally sound proofs, not just statistically sound proofs. It's just here, we're in this context, we're going to convert the GKR, which is statistically sound, to a snarl. Okay, so next I want to just mention, why do we need the GKR? I mentioned that there's interactive proofs already from the 90s. Actually, there's the celebrated IP equals P-space theorem that gives an interactive proof for all of P-space by Shamir. So why do we need GKR? And the answer is that in these interactive proofs from the 90s, the prover runtime, let's say to prove a time t space S computation, the prover needs to run time 2 to the space squared. So super exponential time in the space. So completely, inefficient. And that's where kind of the GKR comes in. So we say, no, let's use a doubly efficient interactive proof, and then we'll convert it into a snarl using the Fiat-Shamir paradigm. Okay, so let me maybe mention a little bit, talk a minute about the GKR protocol. So it's very simple. Essentially, the high level of the protocol as follows. First, it's only good for bounded depth computation. So think of the computation for simplicity as a circuit. The number of layers in the circuit needs to be small, which the reason it needs to be small is because the protocol will grow with the depth of the circuit. So if it's deep, you'll just get a non-succinct, kind of a very long protocol. So ideally think of like polylog depth circuits for GKR. And essentially, here's how the GKR works. It's pretty simple. You take the circuit, you compute the values of all the wires, and then you apply an error correcting code for each layer of the circuit. That's what the prover does. So the prover computes an error correcting code for each layer. And now let's say he wants to argue that the output is 1. Now, how does the verifier check that indeed he's correct? So let's say he outputs, the value of the wire, at the value at layer D, which is the output layer, he claims is 1. That's the prover's claim. What we're going to do, the prover and verifier run this reduction protocol. This reduction protocol will reduce checking the value VD to checking a value in layer D-1. And it will have the guarantee that if the prover cheated in layer D, he, with very high probability, he will also, in the reduction protocol, will arrive to also an incorrect value in layer D-1. And now we do this kind of, okay, we'll run the reduction protocol again and arrive at another incorrect value in layer D-2, and so on and so forth, until we reach the input layer and arrive with an incorrect value in the input layer. And that the verifier can check on its own because he knows the input. So it's kind of reducing the claim layer by layer until we reach the input layer, which the verifier can check on his own. And what the reduction protocol is, I actually do not want to give too much details, but let me tell you, it's basically just a sum check protocol for those who know the sum check protocol. This is really what it is. So that's it. Mainly we use a sum check protocol and like D times. So I'm not gonna say more about the protocol, just wanted to give you a little bit an idea of the structure of the protocol. So with that, let's go back now to the Fiat-Shamir heuristic and say, well, that's very nice. We have a statistically secure interactive protocol that works in many, many rounds. We want a certificate out of it. We can apply the Fiat-Shamir, but how do we know if it's secure? So just kind of jumping to the point, it is secure. We finally managed to prove that it's secure. We managed to prove that it's secure under the LW assumption, and very recently also under the DDH assumption. Again, don't want to say much more about the assumptions, except that they're standard cryptographic assumptions. Okay, any questions before I talk a little bit more about the Fiat-Shamir paradigm? Okay, so actually I want to say a few words about this Fiat-Shamir paradigm, because first, it's really, really interesting, and it's very broad. It's not used only for SNARGs, to say the least. Actually, it was proposed in the mid-'80s in the context of signature schemes. It was used to construct signature schemes. And actually, one of the most widely used signature schemes today, what's called the ECDSA signature scheme, is based on this heuristic. So anyone who has an iPhone or an Android, you use the signature scheme every time you use your phone. And this scheme is based on a heuristic, and we do not know whether it's sound. So this is a bit concerning, perhaps, to some of you. So we really want to understand if this, if it's sound or not. So I was actually obsessed with this problem. I was Shamil's student in Weizmann Institute. And I really wanted to prove the security of the heuristic. First of all, it's super simple and beautiful. And we should understand if it's secure or not. So here's the situation. In practice, it works. Nobody ever broke this heuristic in practice. Okay, but now there's a question. Okay, in practice, but is it secure as a heuristic? And what we showed, this is together with Shafi, many years ago, based on the work of Boaz Barak, that it's not. Actually, we actually gave an example of an identification. Like this method was originally used to convert identification schemes into signature schemes. But we gave an example. Here's an identification scheme. It's secure. And when you convert it into a signature scheme using this paradigm, it becomes insecure. So in other words, what we showed is there's no way to just generically prove soundness of this heuristic. So even though our example was contrived, we didn't break one of the use cases that of the Fiat-Shamir paradigm, but we kind of proved that you won't be able to give a proof of this heuristic in general. Okay, so that was a bit, disappointing. Moreover, and here's what should amaze you. Remember I mentioned there was a first SNARG by Kalai and Mikali from the early 90s? That SNARG also used the Fiat-Shamir paradigm. And guess what? For this SNARG, it was recently broken by Bartusek et al. So what they showed so this SNARG uses kind of a PCP and a hash function in it, and they showed that here's an example of a good hash function, a PCP, that no matter which hash you use for the Fiat-Shamir paradigm, it will break. So even for SNARGs, like for the SNARG of Kalai and Mikali, the paradigm was not good. So why would it be good for GKR? So what distinguishes GKR, for which we managed to prove security, and like Kalai and Mikali, where security was broken? So here is the difference. All our counterexamples for this heuristic started with an interactive protocol that are only computationally sound. So when we broke the Fiat-Shamir heuristic, it was when our starting protocol was computational sound, and we got a SNARG or a signature. So both the the signature scheme started with an identification scheme, which was only computationally sound, and the Keeley and Mikali started with an interactive proof that was only computationally sound. And that's where things were broken. So then we asked, okay, what if we start with a statistically sound proof, like in GKR? Then can we prove security? And so we studied this actually in the general context of statistically sound proofs with Rothblum and Rothblum. And we showed that the Fiat-Chomel heuristic is secure when you apply it to statistically sound proofs, but it was only under very strong hardness assumptions. So it wasn't under standard assumptions like LWE or DDH or things like that. It was under a very, very, very strong assumption. Still, I think breaking that assumption would be interesting, but it wasn't triumph from our standpoint. And recently, building on this work and building on beautiful work of Canetti et al., we managed to prove that actually for the specific GKR protocol and the family of protocols, which includes the GKR protocol, we can prove security of this heuristic under standard assumptions. So let me actually not give any more details and just go for the little time I have left, I'll go to part two. But let me just quickly give you some takeaways from this part, like what you should remember, or I hope you take away from this part, which is we have this notion of doubly efficient interactive proofs where where not only the verifier is efficient, but also the prover has to have not too much overhead. We constructed such proofs for bounded depth computations. We converted into a SNARG using the Fiat-Chomel heuristic, and we proved that for this specific protocol, this Fiat-Chomel heuristic is sound under standard assumptions. And there are many implementations of this protocol. And kind of the bonuses we got on the way is a better understanding of the security of this Fiat-Chomel paradigm in general, which is, again, interesting, not just for the construction of SNARGs. And also something I didn't have time to talk about, but we got applications to other areas in complexity theory. For example, we were able to use this to argue that finding Nash equilibrium is hard, which seems, what the hell is the relation to Nash equilibrium at this point? And again, not going to say too much about it, but there's a beautiful work by Choudhury et al. That show how you can take a SNARG that has special properties, uniqueness and updatability, which our SNARG has, and we can embed it into some PPAD problem for which Nash is known to be complete. For which Nash is known to be complete. And this kind of this connection gives us a hardness of computing Nash. So again, didn't expect you to get much out of this last couple sentences, but we are able to use our SNARG to get Nash hardness of computing Nash equilibrium. Okay, so let me just mention a little bit about how we go beyond bounded depth. So far I showed you how to get SNARGs for bounded depth computations. And in this, I went from interactive proofs, doubly efficient interactive proofs, applied the Fiat-Chomel, and that's how I got the SNARG. Now I want to show you how to get SNARGs for arbitrary computations, not just bounded depth. Okay, based on standard assumptions. Okay, so here's the idea. The idea here is to start with a multi-prover interactive proof, not just one prover. So here's the model. The model is there's a verifier interacting with two provers. And these two provers are not allowed to communicate. That's what gives this model its power. So think of the provers, they're kind of in different rooms. There's a wall between them. They cannot communicate. Okay, the verifier sends them a question. They send an answer, and based on that, the verifier decides if to accept or reject. Any questions? Okay, so this proof system, this proof models of multi-provers or two provers is known to be extremely powerful. And the power, in other words, any t-time computation can be proved where the communication is only polylogarithmic in t. So like exponentially shorter. And verifying is like super efficient. You essentially read the input and do some polylog T computation overhead. And also, the prover's runtime is very efficient. It's polynomial in T, but if you optimize, you can get quasi-linear in T. So really great. And what gives this proof system its power is exactly the fact that there's two provers that cannot interact. And for example, just to illustrate, think of like provers who committed a crime. Okay, they're trying to lie. It's very hard to lie in a consistent manner if you're separated. It's much easier to frame suspects if there's two of them, as opposed to just one. So that's really why it's much more powerful. If you have the two suspects, you put in a separate room, you can do much more. It's much easier to get correctness, to make sure they don't cheat. And indeed, these proof systems work on kind of consistency checks. Essentially what the verifier does, it checks consistency against the two provers.
So just to make sure, we assume that both have access to the same, oh, there is no witness here, I guess.
Okay, actually, right. So in this talk, I'm thinking of deterministic computations, but actually, you can do it also for NEXP or for NP, where the communication is polylog. And in that case, yes, both provers have access to the witness, if you think of the NP version. Yeah, but in this talk, yeah, thanks for the question. But in this talk, I'm mainly focusing on deterministic, and I'll mention why in a bit.
Perfect, thank you.
Okay, thank you.
I have a question.
Yes.
What's an example of an application of a multi-prover interactive proof?
Again, what is an example of?
An application of a multi-prover interactive proof.
Okay, so you're asking, when will we have two provers? Kind of when are we going to use it? So first, you can think maybe, I don't have a good answer, but you can think, maybe you don't trust two people, there's two people you don't trust, and you assume they don't communicate because they don't know one another. Maybe you have very important computation, you use two clouds, one Amazon, one, I don't know, Microsoft, Azure, and you send whatever. I'm making this up, I'm not saying. But I think the reason this is a super, super important and interesting model is because what it gave us, that the applications of this model to complexity theory. So one answer is, this is what gave rise to the PCP theorem, which I'm not going to talk about today at all. But another answer is we can use this to construct snargs. And let me tell you how. So here's a beautiful idea. It's called the BMW heuristic, because it's due to Biel, Mayer, and Wetzel. And here's what they propose. I'm going to say it in the language of FHE, of fully homomorphic encryption, even though fully homomorphic encryption did not exist and they used peer schemes. It's just easier to state it this way. So here's their idea. Their idea is the following. Use just one prover, a single prover. Give him both questions. Now, of course, if the prover knows both of the questions, he can cheat because, as I said, these proofs rely on consistency checks. So if he kind of knows, you can't just give him the two questions. So instead, give them the two questions encrypted. And what do I mean by encrypted? Think of it kind of in a locked box, opaque box. The prover cannot see what's in there. So you give him encryption of query 1, you give him encryption of query 2. Now the prover needs to compute these answers. If you use an encryption that allows you to do computations under the hood without actually knowing what's encrypted, this is exactly what's called fully homomorphic encryption, then he can compute the answers without actually knowing what the questions are, all under the encryption. So the prover will get encryption of Q1. He will compute the answer as P1 would. Without knowing what Q1 is, he gets kind of an encryption and he kind of does the computation of P1 homomorphically under the hood of the encryption. And similarly for Q2. And now the verifier who knows the secret keys will, see the answer and decide if to accept or reject exactly according to V of the multi-prover interactive proof. That's the idea, how you get rid of a prover, and stay with a single prover. Any questions about this heuristic?
Do you have to encrypt both questions to prover 1 and prover 2, or is it sufficient to encrypt just one of them?
Good. You need to encrypt both. And the reason is, if Q1 is in the clear, then when you answer Q2, under the hood, you kind of know both Q1 and Q2. And then you can cheat.
I see.
Because you can do a computation. Yeah, so you need both of them to be encrypted for soundness. Okay, but let me tell you actually, talking about soundness, first note, it's not a snark. It's a 2-message protocol. It's privately verifiable. You need secret key to verify. It's not a snark. Second, it's not secure. So now you should be like, what, first, why is it not? Okay, I'm kind of running out of, okay, no, I have a few more minutes.
Sure.
So, okay.
That's more time.
Okay, so first, why is it not secure? It seems to be secure because when the proofer is answering question 1, question 2 is encrypted. Actually, it's encrypted with another key, a fresh key. He has no idea what's sitting there. So really, when he gives A1, Q2 is like garbage for him. It's encrypted with a different key. He has no idea what's sitting here. It's garbage. So how can he use that? So it seems like, wait, this should be secure. So let me tell you why it's not secure. I think this is a super interesting message, in my opinion, understanding why it's not secure. So here's why. And this message actually had a lot of consequences. We learned a lot from this message as a community. So here's why. What is the guarantee in the 2-prover case? The guarantee is the provers do not interact. Namely, the answer 1 is only a function of query 1. Answer 2 is only a function of query 2. That's the guarantee. Only under this guarantee, this is sound. In other words, the strategy of P1 and P2 is what's called local. It's a local function only of their query. Now, let's see what happens in the single prover setting. Here, what does the encryption guarantee? The encryption doesn't guarantee locality. What it guarantees, that if you look at this answer, it doesn't signal information about Q2. Namely, this answer, it can have encryption of Q2 in it. I mean, the prover sees encryption of Q2. A1 can be encryption of Q2. I don't know, whatever. But when you look at A1, you cannot learn something about Q2 because then it would break the encryption. So the only thing it promises you is some kind of a non-signaling condition. That answer 1 does not signal information about query 2, and answer 2 does not signal information about query 1. This is called a non-signaling strategy. And it turned out that these non-signaling strategies were studied quite significantly in the quantum community. So we kind of found this notion, so this was very surprising to us, that actually encryption, really what it gives you is non-signaling. And so then we thought, okay, so if this MIP had what's called non-signaling soundness, and again, I don't want to define it formally, but if it had this notion of non-signaling soundness, then it turns out we could prove soundness for this. Because really what you need is non-signaling soundness. And then we had to work hard to actually prove, construct a non-signaling sound MIP. But that's how we got kind of this 2-message scheme. Okay, so then, it's still, as I mentioned, it's not a snark. There's a way to go to make it a snark. One way we got a snark is by using special encryption. We called it zero testable encryption. And then one can make it a snark. Again, don't have time to go into it. Another way to make it a snark is to use what's called a barg. I don't have time to go into it, but essentially a barg just says it's for NP. It's a snark for batch NP. You have many NP statements. And instead of giving all the witnesses, you want to generate a small witness, which is the length of one witness. If you had a barg, then we can convert this into a snark. So essentially, one way to get a snark is by taking a barg, and then you can convert this non-signaling MIP to a snark. And then you can ask, okay, do we have a barg? Well, now that we realized it, we do. We started working and everybody came up with bargs. So first we showed actually that you can get a very pathetic barg, like a very long barg of size almost k the number of instances times the witness, because we can kind of boost it to be small. And then there are many bar constructions in the literature. So recently, we have under various assumptions. And so now we have our succinct bar. Okay, let me just skip and go quickly to takeaway. So now we have snargs for any deterministic computation. The reason we're stuck with deterministic is because we only have non-signaling sound MIP for deterministic computation. The classic soundness we have also for non-deterministic, but non-signaling soundness we have only for deterministic, and some subclasses of non-deterministic, but not all of NEXP or NP. And we got these snargs via connections to multi-prover interactive proofs or non-signaling multi-prover interactive proofs. We used this recently to get quantum supremacy. So that was another kind of interesting connection. We got connection between encryption and non-signaling, application to quantum complexity, like the fact that we have non-signaling MIP equals to exp, that the way we constructed this non-signaling MIP, that was kind of an open problem for people who are interested in quantum. And there was some additional bonuses to hardness of approximation of linear programming, snark composition, so on, which I didn't have time to talk about. Okay, so just to summarize, we gave two types of snargs, one from interactive proofs, one from non-signaling multi-prover interactive proofs. Just to say, I think this entire line of work for our community was really a success story. Just seeing kind of the rainbow from very, very theoretical ideas all the way to deployment, I think is very, very, very nice. Now that we're in the process of standardizing all of this, which is exciting. And yeah, I just wanted to end by thanking all my amazing collaborators, including students I've worked with, postdocs, and my colleagues and mentors. And yeah, just say the grand challenge that's remaining here is to construct snargs for NP. The focus of this talk was on P, but kind of taking any NP witness and shrinking it to be of size kind of, let's say, polylog is still a grand challenge that we're trying to solve. Okay, thank you. Sorry, I'm a bit over time, Rachel.
Thank you, Yael. No, it's great. It's great. I mean, you had a lot of questions along the way. Anybody have any questions? If not, there's one in the chat I can ask. Okay, so there's a question in the chat that says so this construction will not be applied to cases like blockchain, right? Can this construction be generalized for multi-provers in parentheses interactive ones? And can using additive homomorphic encryption help instead of FHE?
Okay, wait. Why will it not be used for blockchain?
Grace, Sima, this is your question. So if you want to unmute and I'm clear, please do.
So I can actually answer why one would think they would be not used, but why actually they can be used. Okay, let me talk for blockchain applications. Usually, when we do a payment, verifying this payment is a huge computational burden because it depends on the entire chain. So that's why we want to delegate it. We don't want each to verify the computation. However, the input that you need in order to verify the computation is the entire chain. And we need to read the input. I mean, what can we do? When we check the validity of a computation, we need to know what's the input, what's the computation? And that depends on the entire chain. So it seems like it's not applicable. However, it is. And the reason it is because you can think of and that's how actually this is done, for these blockchain companies, for example, Ethereum. What they do is they hash down the entire chain. So now you have a hash. And now what you prove is essentially that now to verify, you don't need to know the entire input, the entire chain. All you need to know is the hash to verify, which this is now kind of became an NP kind of problem because it's NP because now it's not a deterministic function of the hash. It says that there exists kind of a base for the hash function, which is all the chain, all the blockchain, the entire public ledger, such that when you hash it down, you get the hash value, and said that the computation is correct. So it becomes an NP computation, but we do know how to deal with it. We do have, like our snarks can incorporate that. I just didn't talk about it in this talk. So these are actually used in blockchain applications.
I guess I can ask a question.
Yes, of course.
Can you repeat about the difference between like local strategies and non-signaling strategies?
Yeah, happy to. This is very delicate. It took me a long time to understand this. So a local strategy just says A1 is a function of Q1. A2 is a function of Q2. That's it. Non-signaling, it allows A1 to be a function of both Q1 and Q2. However, if you look at the distribution of answer 1, it doesn't change if you change Q2, which now, okay, so that's the difference. However, now you should say, wait, doesn't it mean that it's local? It seems like it's local. And the answer is no. And that part is very confusing. No, it turns out with non-signaling strategies, you can do much more. And let me give you an example for that, okay? This example is not a very good one, but I think it conveys the idea. Let's say we're two provers and we want to prove that a graph is three-colorable, but it's not. Okay, how will you ask us to prove? Here's a very simple kind of protocol. You would say, okay, you're arguing that it's three-colorable. Okay, color it with colors 1, 2, and 3. Sure. Now you come to two provers with an edge, and you give one prover, one vertex, and the other prover the other vertex, and you make sure that they're colored in different colors. Now with local, I don't know how to cheat. Like I don't know how to cheat with probability 1. I can cheat, but I'll be caught with probability 1 over the size of the graph. Here's a way I can cheat with probability 1 using a non-signaling strategy. What I will do, you give the two provers an edge, like two nodes of an edge, and they will answer with 2 random distinct colors between 1, 2, and 3. Now it's really not signaling, because when you look at one color, each color is random. It doesn't signal anything. But now they cheat with probability 1. So it's delicate. It takes a long time to see why non-signaling has at all any power. But I think this example illustrates a power that non-signaling has that local does not.
So that generally has to do something with the nature of they have an entangled qubit between them. It's sort of what's going on.
You can think of it, but I think yes, you can. But they have more than entangled qubit. Actually, even if they have entanglement, still you can. Two provers with entanglement you can do next. So it's much more powerful. No signaling is really tying their hands, but really what gives no signaling its power is the fact that they have randomness. The fact that the provers can have randomness, that's what gives the non-signaling the power it has.
We have correlated randomness.
Correlated randomness, exactly. Okay. Exactly, yeah.
Interesting. No, that's really interesting.
So is it time for a final question? Just very quick. Thank you. So just I want to get your comments on something. So you mentioned that the PHMIR heuristic is a heuristic and it was recently proved, but to prove it, you have to sort of change the heuristic itself in the sense that you cannot just use SHA-256, right? You need to change what you're using, but people are using SHA-256 and I'm going to continue using SHA-256. So what's your opinion on the analysis of the security?
Good. Okay, great question. So let me just repeat the question. When we proved the security of the PHMIR paradigm, we did not prove it with the hash function SHA-256 or whatever. We gave an example of a hash function. Here's a hash function. If you use this hash function, then you get security. Now, the hash function we constructed to prove security was not efficient in particular. I mean, it was polynomial time, but it wasn't, nobody will use it in practice. In practice, people use SHA-256 or these super efficient hash functions. So now one can ask, so what is the significance of this result? If anyway, people don't use it. So, we didn't prove that it's secure in practice. And you're right. So let me tell you why I think the result is significant. Because now, if someone breaks this heuristic with SHA 256, then we know that the problem is with SHA. Okay, we know, look, this paradigm is secure with some hash function. You don't want to use this one? Fine, use another one. If you use a hash function that's not good, you need to change. The problem is with the hash. It's not with the paradigm. Whereas before, that was not clear. We didn't know, and actually we have examples, that no matter which hash function you use, it will be broken.
No, sorry. Yeah, it definitely makes sense. It's just something that I've seen also happening in the context of, for example, post-quantum signatures and so on, is that there is a security loss from moving from interactive to non-interactive. And this, I don't see exactly how it exploits what the concrete hash function is, more than the fact that you can predict what the challenge will be. I mean, you can compute deterministically what the challenge will be given the input. So for example, I imagine this will apply to your case as well, that there is a concrete, once you look at concrete parameters, there is a loss in security parameters.
Yes, for sure there's a loss. Completely agree. Yeah, this result that proves the security of the Fiat-Shamir heuristic is theoretically interesting. You know, it's not, that's what I'm saying. I'm not advocating to use the hash function we constructed from the paper in practice. I'm really not advocating for that. It's just show. Yeah, so it's mainly a proof of concept, you know, that one can use. And look, to tell you the truth, in practice, these things are not broken. You know, when you tell practitioners, we want to prove security, they're like, it's not broken. So why, who cares? You know, so it's mainly for us to understand what it is that we're using and is it indeed secure?
Got it. You know, definitely makes sense. Thank you so much.
Yeah, thank you.
I think with that, let's thank Yael again.
Thank you, guys. Thanks for the great question.